I mean, it's just like up and down. All right, let's try it again. Okay, thanks you again. So the plan now is to move deep into models. So the rest of the afternoon is models. We're going to be models, models, models with a little dash of visualization salt there in the middle just to keep us awake. The original schedule we're off a little bit because of this morning's traffic snafu, but I'll probably go about 40 minutes on the stat overview and then switch over to diffusion, unless there's a groundswell of support to keep going through this. As is always the case with this place, there's a lot more material here than we probably should be treating in depth, but so we're going to go quickly and go through that again. So my goal in this presentation is to sort of bring everyone up to speed to where Scott and is going to take us for Scott and Carter and Dan and a few others are going to take us to move forward with sort of the statistical models that we do this afternoon, and Nina, and so there's a whole bunch of these other things we're going, and so what I want to do is sort of lay a little bit of common groundwork and sort of give you a sense of what this field looks like without going into great detail. So there's not going to be a huge number of details, but there's going to be a basic idea of what's here, and then we'll jump over to diffusion and see where that's at. All right, so let's start with an overview. So what do I mean by statistical models for networks? So statistical models for networks are really a whole class of ways of thinking about where our networks come from. And these are formalisms that are used to characterize the observed data that we've found. So we've collected data in various and sundry ways, and we've now want to make sense of that data and see how one bit of data we've collected is different from another bit of data. So we need something to compare it to. And so there's this whole world out there of called random graph theory. And so random graph theory and random models for networks sort of builds from a very simple sort of set of ideas about Erdos random graphs, which are adjacency matrices where we flip the coins. And then we put a bunch of different sort of constraints on how we flip those coins, on what sort of parts of the network we're flipping, what parts we're not, and so forth. And that generates a whole sort of series of more and more complex models. And we're not going to go through all of them today, but the social science, and this is not all of them, there are many more out there in the world, but the social science sort of piece that we've gone through is to go from Erdos random graphs to through a series of very specialized graphs, which are essentially row and column contingency tables, to a generalized version of this that then gets merged into a series of exponential modeling exercises. And that became branched and moved into a whole series of models about how attributes affect graphs. I'm in NIH world, everything's a grant. Graphs, right? And so we can think then about this notion of, well, we can condition a network by their attributes. We can compare men to women, boys to girls, what have you. But that modeling tradition was separate from the modeling tradition about rows and columns and contingency tables. And so those became merged in a series of things that are now this whole class of models about exponential random graph models, latent space models, various kinds of association models, additive and linear models. There's a whole series of things that have come out of this. And this world has now just exploded in the last 25 years or so. And it's really a remarkable, you can literally spend your career doing this. And thankfully, we have some people who have done that. So Carter and Scott, for example, have spent a good deal of their time doing this and other substantive things. Nina has spent a good deal of time working on these kinds of models on the diffusion side. So there's a bunch of these things that we can talk about. And again, this is a fire hose, and there's a lot here. So I'm going to try to just quickly get us up to where we're going. Oh, here it is. Yes, so there's a lot of these books, right? So look at these books if you want to read. I heard a really depressing statistic this morning that the majority of American men had not read a book in the last year. Don't be like that, right? So we're not. That's not like we are. But buy a book. They're good books. So find one of those. So the first question is, I think it's particularly those who have come to the networks tradition from a ethnographic sort of perspective or a social problems perspective. The first assumption of classic network analysis is we have the population. Like that's the boundary feature, is that I'm collecting data on every person in the network, and I have it fully and completely observed, and what do I need to infer to? Right? There is no inference problem here, so it's not like I've gone out and randomly sampled 100 people and need to know if that's going to be replicated in the population. And so from a sense in which we have a population sample, there is no, the statistic you get is the truth. That's a perfectly fine description of the sample you have. And if I have the population, that's the truth. There's no inference there. There's nothing I need to do. The problem with that is that in reality, most of the networks we've observed it's very rare for us to have a network where what we've observed is a fixed historical fact that is true for any kind of substantive history or substantive time. If you're dealing with something perhaps like a political network or co-voting or other kinds of or treaties or something that is very heavily historically dependent and each relation is very high cost and high salience, then that sort of historicist, I have the population, there's nothing to infer to, might be true. In most of the work we deal with, which is surveys of people, what we've really drawn is a random sample from people's expectations and experience that they're willing to tell us that day. And so what we have is a graph that is in fact an N of 1, that is a population, but it's really a sample from an unobserved population, a potential population of all possible graphs that are like the one that you drew. And so what I've done is I've gone out and sampled a school, they've given me their network, and on that particular day they tell me something about their relationships and I write them down. And if I were to go back tomorrow, they would tell me something that's probably really similar to this, but not exactly the same. And how similar and how different it is from day to day without any real relational or ontological changes in what people are doing, that's a sampling feature. And that's a sampling feature from not a state space of cases in the world, but a state space of potential cases in the world. It's a probability space that exists out there in the multiverse that we happen to see one version of. Right? So the question we're really asking is, would we see the observed graph if the process were random? Right? And so what we want to know usually is whether or not the graph we've observed is just random noise or it's somehow systematic random noise. So there's always going to be random noise, and the level of random noise we have we want to make sense of. Common association tests like correlations, regression, and source search assume independence, and so if we think about that attribute branch of the graph space, we've sort of violated some of the tests we typically rely on as our decision rubrics for importance. I actually think that's a good thing for us because we tend to rely on those rubrics too much. So the fact that we can safely say those rubrics don't really apply here, so P equals 0.05 is probably not ever going to be exactly right in the world you deal with anyway, but it's certainly not right when our cases are not independent. So we can do that instead is think about substantive things. So I think, again, I'm going to ask you to push yourself towards the substantive side of these questions as opposed to the decision rubrics. So how do we answer this question? How do we get to the point of whether the observed graph we have is something that we would expect to see or something that's a rare event conditional on something else? Well, what we need to do that, we need to calculate the probability of observing this event. And the problem with calculating the probability of observing a network is that the combinatorial possibilities of number of networks that are out there is ginormous. And so we can't enumerate it, so we can't actually get a denominator to know what this is, except for in very special cases. And so what we need to do is some procedure that instead of enumerating the population and then figuring out what our probability is, that would allow us to sort of shortcut that enumeration process and get to where we are. And that's what random graph theory does. Random graph theory allows us to think carefully about the process that generates a network, and thus we can understand the likelihood of observing this or not. So this is a classic. This is a simple random graph, and there are some things we know about random graphs. For example, we know that if it's a simple random graph, if I'm just flipping the edges here independently each time, you're going to have something like very close to a Poisson degree distribution. Closer and closer as you get bigger and bigger. We know in a random graph that we see this kind of a phase transition like I talked about yesterday, that if I keep adding edges to the network, I go from lots of little disconnected points to a tipping point at one point where everybody becomes connected. And magically, biologically, ecologically, evolutionarily, a lot of sexual networks sit right about here, which is why HIV is so hard to predict. So we want to think then about whether or not this random model, which is really, really interesting, is really useful for us or not. And the reason it can be useful in some very specific cases, but most of the time the networks we deal with are not uniform random graphs. They are not, every edge has an equal probability of existing. Some of our edges are much more salient than others and are much more likely to be observed repeatedly than others. And so we need a way to condition that random graph to figure out where we're at. And there have been a bunch of great ideas to do this. And so a lot of these approaches to doing this just say, well, of course the graph isn't random, it's not uniform random, but it's random conditional on the marginals, on the number of ties a person receives or the number of ties they send. So if you think about a chi-square test or a chi-square table, we know what those marginals are, and we expect to see a lot of interactions between a high out degree case and a high in degree case just by pure random chance. And so we can condition on the marginals, on the out degree and the in degree. Or if we're interested in something like triads, we can condition on the known number of mutual asymmetric and null dyads. If my network has no mutual dyads, it can have no complete triads. It's just a necessary feature, right? And so that's a constraint on the state space of what kind of graphs you can get. And so the beauty of those kinds of models, this is the uniform graph given the distribution of mutual asymmetric and null ties here, is that allows me to say, well, is 5 a big number or a small number? If you ask people just generally what clustering in a network looks like, you think, well, 5 ties isn't very many. But it turns out that we would have only expected what we know, to have very, very, very few of these. So in fact, we have 9 times more than we would expect by chance. So is 5 big or small? In this case, conditional on the distribution of dyads, this is pretty high. And that's the kind of FF sentence we want to be able to say. And it turns out once we know the expected value for something, we know the variance for something, we can know the covariance of something, so we can know the likelihood of seeing both 105 1-1 downs and 103 021Cs, whatever those mean. I know, it doesn't matter. But the point is that we know this because we understand these underlying distributions that make possible certain sets of macro level distributions. Now, on the attribute side, what we want to think about is whether or not we can essentially slice the world up. We know we have all this great mathematical theory and understanding and history in modeling uniform random graphs. So wouldn't it be nice if we could just copy that over? And so let's do it by talking about lots of buckets of uniform random graphs. So I know that my entire network, and this is an American high school, a classroom network, and so race structures relations in these kind of schools, so there's a homophily on race, but maybe within race it's random, right? So I can, instead of thinking about one uniform random graph, I can think about 9 uniform random graphs that are the crosstabs of these different things, adjust for the marginals, and I can get a long ways. And that would be one model of where we can generate things. And so example, if we do that, we say that this is the mixing probability on an observed network, and then we just generate a random graph that matches it, I get the exact same mixing method, but you'll see that those are not the same, right? There's something going on here. There's some systematicity to this network that isn't exactly in this network. They're both hairballs, right, no doubt, but there's something missing in this set. Well, we can look at what's missing. In this case, I didn't match on degree distribution, so I should probably do that instead. So the degree distribution isn't right, and we might go through and do that. And the logic of this is very simple. We say, well, this works sort of, but not great. So let's make slightly smaller buckets, right? So instead of just buckets of white, black, and other, let's take white male, white female, black male, black female. And so now instead of 9 random graphs, I have, 12, a bunch more random graphs. I should have counted these. My brain doesn't work up here. And if that doesn't work, let's go a little finer, right? So now instead of having just by gender, I might have dozens and dozens of these categories. And I expect really strong homophily on people who share lots and lots of things, a little less if they share more and less if they share less. Right? And so at this point, I get down to a really fine cell, and that's probably pretty good. And I can somehow characterize the distance between one set or the other, and in fact do away with cells entirely. So instead of saying, do we match, are we the same here, we can say, are we close here? And if I say, how are we close in a lot of really small boxes, I can say, are we close in a uniform space? So I can expand this over. Now, of course, I've pulled a trick on you there, right? Because as soon as I've done this, it's possible to have a uniform random graph in this little cell. It's not possible to have a uniform random graph in an infinitely small space in here. So I've pulled a trick on you there. Just so we're all aware on board. But the logic is the same. What we want to say is there's some governing principle that says the likelihood of a tie occurring within a distance of the diagonal here is a map to how likely a tie is to be in the distance here. And that's the trick that happens. And this, in fact, is a set of models. This is known as the latent space model in networks. And I kind of like to start with the latent space model because it's really, despite the fact that the underlying mechanics are pretty weird and fairly sophisticated, the intuition of this is a nice model. And so the way this model works is it says that there's a probability of observing some graph conditional on some features. And that probability is a function of these two vectors of statistics of the characteristic of I and the characteristic of J, and importantly, the distance between them. And so that's what this says. This says that we can convert this model into a logistic expression of the same thing. And that logistic regression says that the probability of a tie is a function of the absolute value of the difference between these two vectors. So what are those two vectors? Those vectors are something I make up entirely. Right? They are something I pull out of the air in order to maximize this feature. So this is what it means to be a latent space model, is that I have some characteristic, right? In this case, I have, in this way I've written this model, you don't know how many of those characteristics I have. Let's just say it's 1. So we differ on some underlying coolness factor, and the nerds are on one side and the cool people are on the other, and the further away we are, the less likely we are to be friends. Right? And so we can't measure your coolness factor, but because I know that that's driving it, I can let the machine say, let's find every possible factor that could be out there. We don't actually search for it. There's ways to get to it without having to do that. But in principle, we say, let's find all possible ways we could array us on a single dimension that, in fact, maximizes the probability that a tie we observe would be generated at random chance, that it has the highest probability. And these models are well developed. Peter Hoff, who's a professor here in the statistics department at Duke, is one of the core developers of these models. Mark Hancock, Giles, and a few others. These models are really fun to play with. And so you can take an observed network, and what this model says is, let's identify, this is because it displays nicely a two-dimensional latent space model. And we array each point, so monk 12, in this case from the monastery, we put him pretty close to monk 14 because they share a tie, but they're far from monk 1 because they don't share a tie. Now, we run this model because Peter Hoff and the rest of these crew are all Bayesians. They say, well, we don't really know where they are in a single position. We know they're in some cloud of positions that are right here. And so we have some posterior distribution of spaces you can be in, but the odds are good that people are in these positions and those positions drive a tie. And that's a really nice way to end up generating a predictive model for your network. And you can say, is my model, is my network a likely network to see, how rare is it, and so forth, by just generating a very simple fit to a latent space. And this model in R, if you run it, is literally one line of code. That's all it takes to get it. The underlying model is there. It's harder, but that's what's there. Now you can do lots of things with these. Once you have this formalism, you can say instead of having a uniform space that a distance is the same for everyone, I can say that the distance is different by groups. So I might say that whites, blacks, and Hispanics have a different latent space than they do otherwise. And it might be that I have an intra distance and a between distance that are somehow weighted differently. The model will do that on top of it. Now, why do I start with this model? This is because it greatly simplifies your modeling exercise. Right? These are easy models to fit. They're easy models to specify. What's the problem with these models? There is no free lunch. It's easy because it's uninterpretable. It's a black box. We don't really know what Z1 and Z2 are. Like, these could be anything. Many times they're physical space. Go ahead.
Are these functionally similar to variable?
Yes, exactly. So these are, in fact, under the hood, a PCA is the eigenvector structure and what you're used to for singular value decompositions or those kind of things for people who do that. A lot of the thing going on under the hood here for generating these are exactly those, yes. So if you're used to latent variable models in psychometrics, this is a latent space model for just that same idea. So the problem with these models is that I don't know what Z1 is and I don't know what Z2 is. And so from a health standpoint, why go through this exercise if I'm trying to understand the structure of my network? The main reason to do it is that if I care about something like health status, and I want to know whether or not people who share a health status are more likely to be friends than people who don't share a health status, but I didn't measure everything else that can generate the likelihood that we're going to share a friend, I can throw that into the latent space model and then explicitly model homophily on smoking net of whatever else might predict this outcome. So if you want a good conservative test of the likelihood that, say, there's homophily on smoking, then you add smoking as a covariate to whatever kind of model you want to do here, right? And so you can have this model, you can tell the number of dimensions, the number of groups, and then you just add a plus sign there and the thing you really care about. And so it soaks up all that variance. And because it works, it converges, it's sort of a nice way to get some work done and see where you're going. All right. That's in contradistinction to this other way of thinking about where graphs come from, which is to try to identify the boxes themselves. And so the latent space model is an ignorance model, but it's a very effective ignorance model that allows you to get your work done while you do something else. The alternative model is to say, well, I'm actually smarter than that. I've taken, at least one class in networks, since I know something about how they're generated. So let's think carefully about a theory of what generates networks, and then I can figure out which ties are likely and which ties are unlikely. And so if I've observed, this is a toy example. If I've started with a little network like this, the observed adjacency matrix here, the observed ties are 1, and the observed non-ties are 0. The diagonal is ignored. And this is actually a heat map. In the observed network, it's post hoc, so it's 0, 1. You're either as cold as you can be or you're hot. And so a perfect model, and if this were would generate something that looks a lot like this. And so how would we build this model? Well, one way to do it is to think, well, this is a dyadic variable, 0, 1. It's just a logit model. Let's just try this as a logit model. There's good intuition there. And as a logit model of something that would be likely to generate a tie. So what might that be? Well, let's build it up slowly. Let's start by saying that we're going to start with a logit model that all we do is say that ties are equal to the density of the graph. So all we have is what's called an edge parameter or an intercept. And so these are all, what I'm saying is that all of these are 0. So this has a value and those don't. And so that parameter, the intercept edges, is a negative on the log odds scale. And if you translate that out, that says that the density of this graph is 0.24. That's what this thing calculated out would generate. Now that model is true. It tells you that this graph could have come from a network that has a density of 0.24. It probably had to in some sense, but it's very unspecific. So there's nothing about any cell that differentiates one from the other. They're uniform values. Every point has the exact same case. So instead what I might do is, let's say people differ in the ties they send. And so we expect from contingency analysis that we're likely to see more ties on an out row that has a high value than we'd see on an out row that has a low value. And so our model should respect that. And so now we get a little bit of variability. We get to see, for example, that these nodes have about a half a chance of occurring, where these only have about a 0.13 chance of occurring, and it makes obvious sense. It allows us then to fit, or at least more likely on an expectation to fit our rows, but it does nothing for our columns. This is a stupid, you guys are smart, you know where this is going. Let's fit the columns, right? So we can do the same thing, right? So we can do a columns, and we can say, well, why do columns by themselves? Let's do them both. Right, so now we've just done the very simplest marginal effects model. And what we're saying is that there's some probability of a tie that is due entirely to the marginals and nothing else. And now what you're going to notice, and hopefully this was clear as you're watching, is that the bolded numbers are the places where ties actually occurred in our little toy example network. And now you're seeing that bolded ties are in fact pretty common here. So we're seeing that there's a really high likelihood that these two folks have ties, or these 3 ties occurred only because a really gregarious person has a high probability of interacting with really attractive people. And so those 2 things are likely to occur. And so just by pure random chance, we see it, and in fact, we do see it. And so that's an unsurprising interaction given the marginals. Whereas these ties occurred, but this simple marginal model had no ability to predict it. So this is a relatively unlikely tie to occur, but it occurred. So that's a false negative. Similarly, the model would predict that we should see a tie here, but we don't. Right? So we're hitting sometimes, we're missing others. What could account for that? Well, generally, what accounts for it is theory. Right? There's something about in your social system that it makes these people similar or different, or they have some behavior. And I'm just calling this a mystery Q factor that's a dyadic variable, some kind of a distance feature. In our world, it's usually a health-related one like smoking, and we can say that smokers are more likely to be friends with each other than they are non-smokers. And so this is the logic of these models, that we can go ahead and hit these high probability ties, and that's by building up a model a little bit at a time. And these things tend to work pretty well. You miss, of course, sometimes. Some misses are good. right? We don't want to overfit a model. We don't want to have a model that is fit to just one weird case. So we would expect these things to have some amount of variability, but they're informative on these things. And usually what you and I want to do is at the end of the day is say, is this effective? Is this statistically significant? Does whatever this theory thing we care about add to our ability to predict the likelihood of ties in our know? And that is the intuition behind what's known as an exponential random graph model or an ERGM model. And the thing that we're asking is whether or not the graph in question is an element of the class of all graphs with this equation. Is it likely that the graph that I drew could have been generated by this model, by this probability equation that drives the likelihood of a tie? Now, as it turns out, these models are really, really flexible. What you have are a set of parameters on a set of statistics. Right? That's what we've generated, and they're normalized by something that makes it a proper probability. This normalization is a pain in the ass. That's what took all the years to develop these models, right? So I'm going to treat it trivially here, which is, Carter's head just exploded somewhere. But the point is that what we learned in the we learned it first in the 70s, but relearned it in the 90s, was that there's a way to get to this normalizing constant by doing something that is itself not intuitive when you write it down, but intuitive, I hope, when you understand it, which is that you can get rid of this thing in the denominator by carefully figuring out how you specify these statistics. And in fact, we specify these characteristics as change statistics. And so we now have our theta up here that we talked about before, that parameter. But instead of being a theta of the raw z, it's the theta of a difference between the dyad when the tie is present versus when the tie is absent. You're like, well, fuck, Moody, that's kind of a obnoxious thing to do. Like, why would I take a difference on a network? I've already observed it. I don't need to have a difference. Well, you do it because this is actually your underlying comparison. This is the thing you're doing when I'm saying, what is my control group or my comparison? What is the difference between the tie of an effect? So what's the difference of having this versus not having it? So that's where the difference is coming in. And the intuition to think about this is something like an intercept term. So I think there should be some number of terms there. So if the tie is present, I'm going to have a 1. If the tie is absent, it's 0. So for all dyads everywhere in the network, this is 1. A column of 1s in a linear regression is an intercept. Right? So all you've done, we call it an edges parameter because we're saying let's assume the edge is positive or the edge is 0. But in fact, what you're doing is you're adding a column of 1s to your logit model. And what you're getting out of that is an intercept. Now, if it's reciprocity, I can say, is the tie reciprocal? That would be a 1 there. That would be the case that a J nominated I. If that's true, that would be a 1. If J does not nominate I, it's a 0. This thing becomes a dyad-specific reciprocity term. So this value is equal to 1 every time alter nominated ego and 0 every time else. So it ends up being intuitively what you might think naively a logit would be. But the math works out such that these models end up being unbiased estimates of theta. Right? Now, there are some complications. There are some versions of these change statistics that get a little more complicated. But the in general intuition is that when something changes in a way that makes the tie present, you should see more of it. That's the idea. So how does this modeling tradition work? The modeling tradition works by saying you specify what that model is, what those terms of the model are, you fit them, and then you have some sort of a convergence and estimation feature that's under the hood that's really complicated, and you estimate your model of fit. So did I actually have a high probability of fitting the graph I observed? If so, you publish your paper and win awards, get tenure, all those kinds of good things, and otherwise, you go back to the beginning and you do this loop over again. It's a recursive process. Now, it is important to note that this is a fitting function. So what I'm doing is I am specifying a set of terms that I think are a good fit to my observed data. Now, it might be that I could specify a different set of terms that would have the same fit or a very close fit. So this is not a classic rejection of the null hypothesis of a controlled experiment kind of thing. This is can I come up with a hypothetical world that generates a set of observations for which my observation is likely? And that's a subtle difference, because we're all going to interpret it as, can I reject the null hypothesis of the term I put in? But other models could predict your data just as well as it's possible that other models would predict your data as well as the model you specified. They would be equivalent in their their prediction, just in the same way that there's lots of ways to get two numbers to add up to 10. There are lots of ways that a model can be specified that can fit a graph. And so you just need to be aware of that, and this is part of your job as an analyst to know that you're including the relevant ones as opposed to the irrelevant ones. All right, what time is it? That's what this is telling me. I'll spend a little bit of time. I gave myself 10 more minutes. I just want to jump a little bit to what these things are doing. This is how the model is fit. When I say goodness of fit, the reason that that sort of model specification ambiguity is important is that at the end of the day, what the field has sort of converged on for coming up with fit are, in addition to the traditional model-based things like the maximum likelihood, the log likelihood scores or AICs or so forth, in addition to those, you want to know, can I predict things from the model that weren't in the model originally? And so if I have a model that has some homophily terms or something like that, then what I want to do is ask a question about the structure of the networks that this model is generating and say, does my model, these box plots here, capture these things that weren't originally in it? So in this case, it's the distribution of distances in the network. So any graph that I've observed has a set of shortest paths, and we know what that entire distance of shortest paths are. And I haven't put a shortest path term in my model. I've put lots of other things in there. And so this is an out-of-sample prediction. And if my model, if these things are effective at capturing the important structure of this network, then this line should fall within the reasonable bounds of this line. Right? And this model, it's, I underpredict the number, I overpredict the number of isolates in this model. I'm underpredicting the distance distribution, so nodes are closer in this network than I've observed there's in the others. That's usually a hint that there's clustering in the network that's not in my model. Because I'm assuming there's a lot more short paths than there are in the real world, and in the real world there are a lot more longer paths. We can see that I've the number of triads in the model I've kind of fit pretty well. The in-degree distribution I fit pretty well. The out-degree I fit pretty well. Not great. There's a bump here, and there's a bump here that I haven't hit right, but there are issues to that I can play with. And so what you do as a modeler is you go in and say, okay, that's what I missed. Well, what would I add to this model to make it work better? And in this case, I added with this thing, which is a closed triad term. And so this just says the likelihood that a friend would be a friend. And when I do that, that captures the clustering in a way that improves some of these degree fits and certainly includes the distance fit. Right? Please, Nina.
Sorry, I'm trying to refer to the lady.
Oh, yes, please. Please go ahead. Yeah, Nirmana. No, thank you. You get tunnel vision up here for that. It's necessary to go. Please.
I was curious with, I guess I've been thinking a little bit about stochastic block models and the way that you could like if you have composite things. As what I've understood so far, we've been mainly talking about the dyads, but can you use this kind of inherent logic to then find maybe like underlying groupings or other sort of
Yes. So the short answer is yes. And the longer answer is a stochastic block model is the generative version of that crosstab I showed you of race by ties. And so so in fact, I'm not going to skip back all the slides because I have too many, but that big, ugly mixing matrix is in fact a stochastic block model. And so you can either fit it to the data where you know what the attributes are, or you can ask it to find the attributes for you. I'll talk a bit more about this on Friday. I have a love-hate relationship with stochastic block models because in theory they work beautifully. In practice, we don't live long enough for them to converge. So we need to find a way to shortcut them, and every one of those shortcuts fails. So this is why. But yes, it's a very good idea. It's just that once the quantum computing comes out, we'll be able to run these chains long enough to make it really fit. But all right. So I haven't talked about a lot of things in this model yet, but there are a lot of beautiful things you can do with these things. You can add all sorts of different features. You can mix and match things if you want. You can add latent features or not. The new models have all sorts of corrections to them that allow you to do things that social scientists are used to. Like we can add interaction terms. We can fit different models for different groups. We have hierarchical models. It handles on-the-fly missing data, so you can just plug NAs into your model and have it work. more or less well. And so like these models have become incredibly beautiful because they're built on a foundation of Bayesian statistics and exponential modeling, and Bayesian statistics is really well developed. And so we're able to borrow all of the ideas of those sort of models and put it into these network models. So it's been a huge advantage. There are still some things in which these models defy our intuition, and it's probably worth the last 5 minutes here to think about it, which is this characteristic of network models which is called degeneracy. And degeneracy is a problem where you run a model and you get through and you get a table at the end of the model that looks something like this, where you get all kinds of coefficients, and I say, look, my closed triad parameter is positive and it's significant, life is good, I go home. The problem is that when the model has to fit the number of closed triads on aggregate, on average. And if you were to go back and ask this model to generate a random sample of networks from the implied model, you'd look at this distribution and you wouldn't see a nice, beautiful, smooth thing like the number of edge problems. You'd see one big bar at 0, one big bar at 10. You go, what the heck's going on there? And that's because what's happening is the graph under the hood is fitting an empty graph, or predicting an empty graph, or a complete graph, and the average of the ratio of the empty graphs to the complete graphs gives you exactly this 0.7, right? Why would it do that? That sucks, right? That's nothing like our intuition from OLS. And the reason is because the simulation process under the hood, this MC-MC chain, where you're going through and you're flipping ties on and on, the model's trying to find where the parameter is. And it's trying to do that by fitting a sign to some kind of a statistic like this. And so I want my closed triads to be positive. And so it's going to keep going in the way of positive. And so in a world where we expect that a friend of a friend should be a friend, then what that's telling the model is that more friends are better. And every time I create a friend, anybody they're connected to should also be a friend. And so you get this rapid snowballing. And so what the model says is if the world looks like this, but in fact, it's never the case that that's true, because the world doesn't look like a linear line. It looks like a diminishing marginal return line. A friend of a friend should be a friend, but I can only have so many friends, right? And so some friends of friends are just acquaintances, and some friends of acquaintances are strangers. And so this is how our world works. And so we need some way to say that there's not an infinite positive return to triangles, there's a diminishing marginal return to triangles. And this is what we call the geometrically weighted edgewise shared partners parameter. And you're going to see a lot of these GW parameters. All of these parameters are designed to fit this nonlinear function. Because the networks have this tipping point and snowballing sort of feature under the hood, where compounding effects compound more, you end up having to tamp that down some way. So you do that by having these kinds of diminishing marginal returns things. And so what that means for you as an analyst is that our intuition from OLS, which is general linear additive models, and it doesn't really matter if I have a hump in the middle somewhere, a straight line's close enough for government work. In this case, it's not close enough. Like, these models will go off the rails if you misspecify them. So they have to be specified properly. I think that's good for science, right? That allows us to think carefully about what we do, but it also means we have to think about this ex post part of the modeling exercise. So we can't just stop at the significance table. We need to generate some samples from your model. You need to see whether or not this model is actually producing the thing you think it's producing. And it's probably not, because none of us have multidimensional intuitions. We just can't intuit this stuff as well as we think we do. The other thing to keep in mind is you got to be patient. These models take a long time to converge, and there's a pernicious feature of getting packages in R, which we've learned as part of our IdeaNet, which is that you can't have your vignettes take longer than 5 seconds to run when R uploads them to CRAN. And so what that makes all of us do is set our defaults to small numbers so that we can post it on CRAN. But then that means the default that you're using is probably too small. So what you need to do when you specify these models is there are a series of control parameters. I thought I had an example here. Yeah, there we go. Where you want to take the interval and the number of sample size and things like this and jack them up through the roof, right? Because the defaults are too small and you will get unstable estimates. So just something to know about. All right, there's a bunch more of this, but I think it's in the interest of time, and we have a bunch of things that are happening later today. I wanted to give just a plug for these basic sets of ideas and let you know that in the slides that are on the set, there's a whole series of different generalizations of these things. Questions or comments or thoughts on the general intuition of this modeling framework? Because this is going to underlie SOUMs or stochastic actor-oriented models. It's going to underlie ERGMs. It's going to underlie relational event models. There's a whole series of these kinds of models that happen. So I want to make sure that you have the same basic intuition. And if those who are experts more than me know that I said something stupid, now's a great time to correct it. Thoughts, reactions? The other side of this is that this has been, and I don't want to, there's 1,000 of these different models in here. I'm not going to go through them all. But one of the beauties of this is that back in the old SAS days, for people like myself, writing a simulation of a network was a really hard thing to do. It took a lot of work to write that model and to get it right and to get things working well. And what we ended up doing was essentially stochastic block models that are on very fine grain. Now what you can do is you can just literally say I want to simulate a network as a function of a formula that I fit. So I can write down a formula, generate the network, and I'll get them out. And so if you want to do the kinds of simulation games where you ask, well, where's the diffusion model going to go? What's the likelihood that I get clusters of one kind or next? You can play those kinds of network simulation games now in a much easier way than you could ever do 100 years ago. And if you want to find a way to test your other parts of networks, this is a great way to do it. So if you want to, one of the problems of general network analysis is because it's so expensive to do, we rarely have ground truth to compare our methods to. These models allow us to generate pretty complicated ground truths that we can then apply our methods to see if they uncover it in the right way. So just a plug for doing that. All right, I'm going to skip some of this other stuff now. I'm going to shift gears and go over to diffusion. Is that okay for folks? Please. Yes, you can. And the way you do it, it's kind of a fun little trick. So the short answer is yes. The long answer is it's not really what you're doing. So what you're actually doing is you're taking that big adjacency matrix and you're putting each ego network down as a block diagonal down that adjacency matrix and setting all the between ego ties to structural zeros. So under the hood, it looks like you're fitting a very highly constrained global network with a set of parameters that are specific to each sort of star in that row. But it turns out that these are really nice. And that's a conceptual way to do it. They do smarter things than that under the hood. They don't actually generate something that large. But that's the conceptual idea. And the beauty from that is that you can then turn off the structural zeros and simulate networks from ego networks. And this is one of the beauties of this set of modeling techniques, is it allows us to take all of the security, IRB, privacy sort of advantages of ego network analysis to collect that data and then generate from it global network data and ask what are the implied characteristics of global networks from those ego network sets. The one problem is, it's like, what are the global networks constrained to the things you can observe on a diameter 2 graph? So because every ego network is ego and one step to alters, there's a lot of structure in the global network that you miss. And so you want to make sure when you do that exercise that you do it in a setting where attributes are highly constrained the graph and where you have a good series of information about what those attributes are. Go ahead. Right, no, it does not. You can have ego networks that overlap in this framework really well. Again, there's an overhead to it because then you have to specify by hand where those cross things are at, and so you have to essentially go under the hood and clean up that giant adjacency matrix. But yes, it's possible. Most of the time, it's not. Again, it all depends on the level of overlap in your set. But it was actually developed because Martina Morris and a few others who were working on sexual networks wanted to find ways to go in and collect data in a privacy way that respected all of the sort of anonymity of respondents, but yet told us something about what the global sexual network works like. So all of this work came out of that. All right, so we don't have to change the